Hello everyone, welcome back. I didn't expect so many of you will be here. I thought all of you will be at the hackathon. You should go to the hackathon. That starts at 7, yeah? Okay, so before we start the class, just a reminder on your midterm test. It was open on Saturday and it is going to close this Sunday, yeah, midnight. So please remember to attempt your midterm test. As of this afternoon, I realized that there's only 65 attempts so far. That's not even 50%. And it's already Friday. What were you doing? Yes, it's week 7. Any plans next week? Going back home? Have a safe journey, drive safe, stay awake until 3 a.m., sleep until 4 p.m., repeat, okay. That's a good retreat for you. I'm happy. Do assignment, okay, that's nice. Some data transformation to my data set during midterms. Are my mark going to be deducted? No. It's not going to be deducted. Start the assignment. Okay, start the assignment. I think it's a good time to start. What are the differences between regression metrics and evaluation metrics? What is your question about? Do you mean the differences between? I'm not too sure. You mean the evaluation metrics between regression and classification? Is it? Is prediction score equals to model performance? I'm not too sure. Maybe you want to rephrase your question. Question 2 of midterm mentioned that the baseline linear regression model. So is it means that the model must be baseline? Just build any model as the baseline model, okay? Found job. Oh, congrats. Hi. Party. Have fun, enjoy. Okay, so again, please remember to attempt your midterm test. It will still be open until this Sunday, midnight, okay? If anyone requires an extension, let me know. But it shouldn't be after week 8, yeah? So this week we are going to cover another classification model called support vector machines. So this is by far my favorite classification model here. So a little bit of recap before we start the class today. So last week what we discussed was logistic regression. So what we mentioned during logistic regression is the way or the intuition of how this logistic regression is making a decision to classify things between class A, class B, or even multi-class classification. So we mentioned that this logistic regression uses a sigmoid function to transform the output to a value between 0 and 1, which represent the probability of any event happening. So it is going to give you the predictive output as the one which is having the highest probability. So that is what we have come so far. And for today's lecture, we are going to cover a topic called support vector machines. So in the discussion of support vector machines, we will cover a little bit of things that you need to know, which include what is margin, decision boundaries, and support vectors. So these are some of the vocabulary or terms that is highly related in order to understand how support vector machines work and what is the intuition of support vector machine. Then we'll also come to learn about this term called hyperplane. So hyperplane is a way of how this support vector machine produce as a decision boundary to classify between classes. Hinge loss function is the cost function of support vector machines that helps these support vector machines to adjust its weights. Then we'll come to discuss this regularization parameter C, a parameter that helps to regularize support vector machines, and how this regularization parameter helps to remove the outlier sensitivity of support vector machines, SVM. So then, before we end the class, we will discuss what is kernels. So kernels is a trick that makes support vector machines really powerful classification model. So let's start with support vector machines. So what is support vector machines, SVM? So it is a supervised machine learning model, and which can be used for classification or regression. So they can be used for both classification and regression, but it is mostly used for classification problems. So how it makes a decision between differentiating class A to class B or more than two classes is that it will construct a hyperplane. Hyperplane is a surface such that it has the largest distance to the nearest data points called support vectors. So we are going to elaborate a little bit more on how this SVM makes a decision to draw these decision boundaries. So as an introduction, this SVM, again, it constructs a hyperplane such that it has the largest distance to the nearest data point. And the difference between this support vector machine to logistic regression, as we discussed, is that logistic regression, it makes a decision that is based on the maximum likelihood of the training data. Yeah. So logistic regression is a probability-based model, whereas this support vector machine, what it does here is it is a nonlinear model. What it maximizes here is not the probability, but the margin between the two classes. So what it's trying to do here is to maximize the region between the two classes, the region that differentiate between two classes. Okay, so what is a little bit of vocabulary regarding this support vector machine? The first one is support vectors. So what is support vectors? Support vectors, they are the data points that lies nearest to the hyperplane. So we mentioned that hyperplane is the decision boundary which this support vector machine tries to figure out. And these support vectors are referring to the data points which are closest to these decision boundaries. So if this data point changes, the position of this hyperplane itself will also change, because how this SVM draws this hyperplane is by identifying the support vectors. Yeah. So now say, for example, if you were to have the same data set over here, we can see that we have data points of class A and class B. So now what this SVM is trying to figure out is the hyperplane. So hyperplane is the decision boundary with a certain level of margin on the left and on the right. So how do we draw this margin is through its support vectors. So it is going to figure out what is the best decision boundary based on the support vectors. So the distance between your decision boundary and the support vectors will be the margin of which makes the hyperplane of these support vector machines. Okay, so what is margin? We mentioned about margin. Margin ultimately is a buffer. So it is the distance between our decision boundary and the closest data points from each class. And the data points from the closest data points from each class is called the support vectors. So now these two dotted lines on the left and on the right hand side of our decision boundary is the margin. So if you still remember, the decision boundary is exactly the same as how we are trying to produce or how we are trying to find using logistic regression. So by switching from logistic regression into using SVM as your classifier means that we are not just trying to figure out the decision boundary, but at the same time, we are also going to figure out the margin of this decision boundary to the nearest data point called margins. So now, all together, we have decision boundary and margins that would make up a hyperplane, which is the entire decision boundary of what this SVM is trying to figure out. Okay, so next, what we are going to cover is how this SVM makes an intuition in terms of classification using this margin. So in SVM, again, the margin is the distance between our decision boundaries and the closest data point, right? So now, what we are trying to do as we train these support vector machines is that we are trying to maximize the margin in order to create a classifier that is less sensitive to noise and outliers in the data. Okay, so in order to maximize this margin, what we are trying to do here is to prevent overfitting at the same time without even regularizing it. So we are trying to maximize the margin in order to help prevent overfitting before our regularization steps. So maximizing this margin according to SVM, the theory of SVM, maximizing this margin is good because it implies that only the support vectors will matter, whereas other training samples are just ignorable. So what it's trying to find out here is what are the support vectors, what are the data points that best describe the boundary between the two or more classes from our data set. So then, after it figures out, it will try to find out a way or a decision boundary that has the largest margin, largest buffer between the two classes. So it is maximizing this margin in order to find out the best hyperplane that defines the differences between the two classes. Okay, and that is the intuition of SVM according to maximizing margin. So a quick question before we proceed. So we talk about this decision boundary and how this SVM is trying to maximize the margin in its training process. So there are two hyperplanes here. Between A and B, which hyperplane gives a larger margin? This is to make sure that you understand the meaning of margin that we have been talking about. Okay, so yes. So this A decision boundary A or hyperplane A have a larger margin compared to this decision boundary B because it has a larger distance from the support vectors. So support vectors here refers to the data points that is closest to the decision boundary. And the rest of the data points, according to SVM, are not so important. Okay. So next, another vocabulary that we want to introduce as we discuss this SVM is called the hyperplane. So hyperplane can be a line, a dot. It can be a dot, a line, or a plane that separates between the two or more classes of instances that we are trying to classify in our data set. So say, for example, if we were to have this data set, we have churn, we have non-churn, we have data who is tagged as class 0 and class 1. So then we have a decision boundary, which is a line, and the surface or the surface between the two margins, maximum and minimum margin, will be the hyperplane. Okay, so now altogether, this surface will become the decision, so-called the decision boundary of this SVM, and what this SVM is trying to figure out. So now that we understand what is hyperplane in SVM, so let's talk about how this SVM works with hyperplane. So this hyperplane is ultimately what SVM is trying to figure out to separate our data into two or more classes. So we have also mentioned that this hyperplane is a space, it is a subspace, or it is a surface. So it can be segregated into multiple higher dimensional space as we add on more and more features. So it is going to construct a flat subspace, which is not a flat surface when it is plotted or mapped to a higher dimensional space. Okay, so in a two-dimensional space, we can see that from the example we showed earlier, the hyperplane is actually a line. Okay, so it's just a line. And in a three-dimensional space, this hyperplane is ultimately a plane or a surface. So in general, if let's say we were to map this SVM or this hyperplane into more and more dimensions, it will form a subspace of dimension n equals to 1 within the space of our data points. Okay, so ultimately these spaces are the margins between each of the classes of data points that we are trying to segregate. Yeah. So now, what is the cost function of this SVM? So the cost function, again, it's the function or the error term that help this SVM to decide or to find the best line that separates the two classes. Okay, so now what we are trying to do here is to try to include the largest boundary possible, and the cost function for SVM is the hinge loss function. If you still remember, the linear regression, what is the cost function of linear regression? Starts with S. Sum of squared residual. So in this SVM, the cost function is called the hinge loss function. So this hinge loss function is a function that is used to train SVM. It is a way of representing the error which this model is seeing during the training process. Okay. So now, what is hinge loss function? So hinge loss function uses the distance between our decision boundary and the closest data points from each class to penalize the model more when it misclassify a certain class. Misclassify a certain class. So what we are trying to do here is to try to minimize the hinge loss function in order to maximize the amount of correctly classified instances. So what we are trying to do here is to minimize the number of misclassifications and maximize the distance between the two classes. So there are two things that we are trying to figure out. First is minimize the number of misclassification, and number two, maximize the distance between the two classes. And how it is making this decision is the trade-off or the balance between the two. And this will make SVM so much more powerful compared to logistic regression, and we'll come to an example in the later slides. So before we move on, quick question. What is cost function? It's a function that measures the error of machine learning model. Yes. It is actually also a function that measures the performance of machine learning model. And it is also a function that measures the distance between the predicted and actual values. They are all of the above. Okay? Understand? Okay. Okay, so now we mentioned that the trade-off between how this the trade-off of how this SVM is making a decision by trading off between maximizing the correctly classified classes as well as the decision boundary, it makes it very powerful. So now let's take a look at this example. So if we were to have a set of data where the classes are segregated between this distribution. So now, at your sense, which decision boundary do you think it's best in segregating between the two lines? It's the left one. Nobody says it's the right one. Why is that so? Both of them have zero misclassification. Okay, so now every one of you here, I guess it's an SVM. So now, so both of this model will be equally good if, let's say, we are judging this, we are evaluating this in terms of logistic regression. Because how this logistic regression makes a decision, it's by maximizing the probability of a certain classes in a certain class. And both of these lines will give us the same output. Yeah, because the probability will just be the same. None of the instances are misclassified. However, we mentioned that this SVM, it's doing two things. So it is trying to figure out a decision boundary that best separates the two classes, and at the same time figure out which is the best decision, the maximum margin between the two classes. So it is just not drawing a line, but also another two lines that buffers between this decision boundary. So I hope by this example you begin to understand how this SVM differs from our logistic regression. So now let's take a look at another example over here. So now say, for example, we have this data set and we have a new instance coming in. So now this new instance happen to have a relatively low phone usage, but the classes refers to pink color class. So in this case, which line do you think it's the best decision boundary? Any more? Okay, seems like we have a half-half, right? So now, the point here is that we are not too sure whether this point is an outlier or is it a legitimate instances. So even if it is a legitimate instances, it could be just an outlier in a sense. So now, if we are a logistic regression, which is trying to figure out or maximize the probability of certain instances, then we may say that, okay, this line is the best line. However, if you were to train a classification model using SVM, the intuition says that this could be a better line because what it is trying to do here is not just to maximize the correctly classified classes, but at the same time, it is also trying to figure out the maximum margin that it sees. And which is why this mechanism of trading off the two objectives makes this SVM extremely robust to outliers. So they are by nature not sensitive to outlier themselves. Okay, so now this leads us to another topic that we want to talk about today, which is outlier sensitivity of this SVM. So we mentioned that this hinge loss function is trying to minimize the misclassification, at the same time maximize the distance between the two classes, and therefore this gives this SVM the regularization ability to be robust towards our outlier. It becomes not so sensitive to our outlier. So before we move on, we talked a lot about this regularization in the past. So what is regularization? This is also in your midterm test. Did you really read it? Or did you just make a guess? Okay, so what is regularization and why are we doing regularization? So ultimately, the reason why we are doing regularization is to try to make our model more generalizable, right? We are trying to reduce the complexity of our model. And therefore, it is a technique that is used to prevent our machine learning models from overfitting to our training data. At the same time, it is also a technique that is used to improve the generalization of the performance of our machine learning model. And at the same time, it is also a technique used to reduce the complexity of our machine learning model, hence all of the above. Yeah? So, what is the regularization of this SVM and how this SVM regularize? So we mentioned that whenever we do regularization, we are trying to add on a penalty clause to the cost function to penalize every single error that it is making. So the regularization parameter in SVM is the C parameter. So what this C controls is the trade-off between maximizing the margin and minimizing the misclassification. So it is controlling, it serves as a threshold or a value to control the trade-off. So whether we want to relax it or do we want to strictly follow the minimization and maximization. So it penalizes all the values that are outside of the margin, which is the distance between decision boundary and the closest data points from each class. So in the chart over here, we mentioned that the support vectors are the points that is closest to the decision boundary or the margin.